Imagine a world where icy moons hide vast oceans teeming with secrets of life beyond Earth. Jupiter's moon Europa is one such enigma, captivating scientists and dreamers alike. The Europa Clipper mission is set to embark on a daring adventure, aiming to unveil the mysteries lurking beneath Europa's icy shell. As the spacecraft journeys through the harsh radiation of Jupiter's domain, it seeks to answer the ultimate question: could Europa harbor life? Join us as we follow Europa Clipper's quest to uncover the truth about this enigmatic moon and its potential to rewrite the story of our place in the universe. The Europa Clipper mission, spearheaded by NASA, represents a groundbreaking endeavor to explore Jupiter's icy moon, Europa. Slated for launch in the mid-2020s, this mission aims to investigate Europa's potential to support life. Europa has captivated scientists for decades due to its subsurface ocean, which lies beneath a thick crust of ice. This ocean is believed to contain more than twice the water of Earth's oceans combined, making it a prime candidate in the search for extraterrestrial life. Europa Clipper will be the first mission dedicated to an in-depth study of Europa, following in the footsteps of the Galileo spacecraft, which provided tantalizing hints of its watery interior in the 1990s. The mission will involve multiple flybys of Europa, leveraging a suite of sophisticated scientific instruments designed to probe the moon's ice shell and underlying ocean. Key aspects of the mission include detailed reconnaissance of Europa's surface and subsurface, analysis of the ice shell's thickness, and the search for possible plumes of water vapor erupting from the surface. By examining the composition and characteristics of these plumes, scientists hope to gain insights into the moon's ocean chemistry and potential habitability. Europa Clipper's instruments will also study the moon's geology, mapping its surface in high resolution to identify regions of interest, such as chaotic terrain where the ice crust has been disrupted, possibly by underlying water. Additionally, the mission will investigate the magnetic field and gravity anomalies of Europa, offering clues about the ocean's depth and salinity. The data collected by Europa Clipper will not only advance our understanding of Europa, but also inform the search for life elsewhere in the solar system. By studying Europa's ocean, scientists hope to uncover parallels to Earth's own deep-sea environments, where life thrives in the absence of sunlight, supported by chemical energy from hydrothermal vents. The Europa Clipper mission, therefore, stands at the forefront of humanity's quest to determine whether life can exist beyond our planet. Europa, one of Jupiter's largest moons, holds a special place in astrobiology due to its potential to harbor life. This interest stems from the presence of a subsurface ocean beneath its icy crust, which is thought to contain more water than all of Earth's oceans combined. This ocean, shielded from the harsh conditions of space by a thick layer of ice, provides a stable environment that could support life. The potential habitability of Europa's ocean is bolstered by several key factors. First, the ocean is likely in contact with the moon's rocky mantle, creating conditions similar to those found in Earth's hydrothermal vent systems. These vents, located on the ocean floor, release heat and chemicals that can sustain life without sunlight, suggesting that similar processes could occur on Europa. Second, the icy shell of Europa is believed to be dynamic, with surface features indicating active geological processes. These include chaotic terrains where the ice appears to have been broken and refrozen, suggesting that the ocean interacts with the surface. Such interactions could transport nutrients and energy from the ocean to the surface and vice versa, creating a potentially habitable environment. Additionally, the detection of water vapor plumes erupting from Europa's surface by the Hubble Space Telescope further supports the idea of an active ocean. These plumes provide a direct method to sample the ocean's composition without having to drill through the ice, offering clues about the moon's potential to support life. Understanding Europa's habitability also involves studying its radiation environment. While Europa's surface is bombarded by intense radiation from Jupiter's magnetosphere, its subsurface ocean is protected. This makes the ocean a more stable environment where life could potentially thrive, shielded from harmful radiation. The significance of Europa in astrobiology extends beyond the moon itself. Discovering life, or even just the potential for life on Europa, would have profound implications for our understanding of life's distribution in the universe. It would suggest that life can arise in diverse environments, increasing the likelihood that life exists elsewhere in our solar system and beyond. Thus, Europa stands as a beacon of hope in the search for extraterrestrial life, driving scientific exploration and curiosity. The Europa Clipper mission is designed to explore Jupiter's moon, Europa, with the primary objective of assessing its potential to support life. The mission's goals are comprehensive, addressing key scientific questions about Europa's ice shell, subsurface ocean, and overall habitability. One of the central objectives is to characterize the ice shell and the subsurface ocean. Scientists aim to determine the thickness of the ice, its composition, and the dynamics of its interaction with the underlying ocean. By studying these interactions, the mission seeks to understand how material from the surface and the ocean may exchange, which could provide clues about the potential for life in the ocean below. Another crucial goal is to investigate the composition and properties of the surface and subsurface. Europa Clipper will analyze the surface's chemistry, looking for organic compounds and other chemical ingredients essential for life. The mission will also focus on identifying salts and other materials that might have been brought up from the ocean below, giving insights into the ocean's composition. The mission also aims to study the geological activity on Europa. By mapping the Moon's surface in high resolution, Europa Clipper will identify regions of recent or ongoing geological activity, such as areas where the ice crust has been disrupted. These regions are of particular interest because they may indicate areas where the ocean and surface are interacting, which could be key to understanding the habitability of the Moon. Additionally, Europa Clipper will investigate the Moon's internal structure and composition. The mission will use magnetometers and gravity measurements to study the ocean's depth and salinity, as well as the structure of the ice shell and the rocky mantle beneath it. This data will help scientists understand the Moon's overall geophysical properties and how they relate to its potential for supporting life. Understanding Europa's radiation environment is another important objective. Europa is exposed to intense radiation from Jupiter's magnetosphere, which can affect the surface and any potential life forms. The mission will measure the radiation levels on Europa, providing crucial information for future missions that might land on the Moon or explore its subsurface ocean more directly. Overall, the Europa Clipper mission aims to gather detailed data that will inform our understanding of Europa's habitability. By addressing these objectives, the mission will help determine whether Europa could support life, advancing our knowledge of potentially habitable environments beyond Earth. The Europa Clipper mission is equipped with a suite of sophisticated instruments and technologies designed to explore Europa's potential habitability. Each instrument plays a crucial role in gathering detailed data about the Moon's ice shell, subsurface ocean, surface composition, and geological activity. One of the key instruments is the Europa Thermal Emission Imaging System (ETHEMIS). This thermal camera will map the temperature of Europa's surface, identifying regions of recent or ongoing geological activity by detecting thermal anomalies. It will help scientists understand the Moon's thermal properties and pinpoint areas where the ice may be thin or where the ocean might be interacting with the surface. The Europa Imaging System (EYES) will capture high-resolution images of Europa's surface, providing detailed maps and identifying surface features like ridges, cracks, and potential plume sources. These images will help scientists analyze the geological processes shaping Europa and select regions for further study. The Mapping Imaging Spectrometer for Europa MASI will analyze the surface composition by measuring the reflected light across various wavelengths. This spectrometer will identify organic compounds, salts, and other materials, offering insights into the chemistry of Europa's surface and its potential connection to the subsurface ocean. The Europa Ultraviolet Spectrograph Europa UVs will detect and analyze ultraviolet light emitted from Europa's surface and atmosphere. This instrument will search for plumes of water vapor and other gases, providing direct evidence of ocean surface interactions and the composition of these emissions. The Radar for Europa Assessment and Sounding. Ocean to Near Surface Reason is a powerful ice-penetrating radar designed to probe the thickness and structure of Europa's ice shell. It will map the subsurface layers, identifying variations in ice thickness and searching for potential pockets of liquid water within or beneath the ice. The Europa Clipper Magnetometer ECM will measure Europa's magnetic field, helping to infer the properties of the subsurface ocean, such as its depth and salinity. By studying the induced magnetic field caused by Europa's interaction with Jupiter's magnetosphere, scientists can gain valuable information about the ocean's characteristics. The Plasma Instrument for Magnetic Sounding PIMS will work in conjunction with the magnetometer to study the plasma environment around Europa. This instrument will help characterize the Moon's interaction with Jupiter's magnetosphere and its effects on the surface and subsurface. The mass spectrometer for planetary exploration MASSPEX will analyze the composition of Europa's thin atmosphere and any plume material. It will identify various gases and organic molecules, offering clues about the ocean's chemistry and potential habitability. The Surface Dust Analyzer SUDA will detect and analyze tiny particles ejected from Europa's surface, providing direct samples of the surface and subsurface materials. This instrument will help scientists understand the composition and distribution of surface materials. Together, these instruments and technologies will provide a comprehensive understanding of Europa's ice, shell, subsurface ocean, and potential habitability, addressing key scientific questions and advancing our knowledge of this intriguing moon. The Europa Clipper mission, set to launch in the mid-2020s, represents a significant milestone in the exploration of Jupiter's icy moon, Europa. The journey to Europa involves several carefully planned phases, each critical to the mission's success. Launch and cruise phase. The mission will begin with the launch of the Europa Clipper spacecraft from Cape Canaveral, Florida, aboard a powerful rocket, such as the Space Launch System SLS or a commercial launch vehicle like SpaceX's Falcon Heavy. Following the launch, the spacecraft will enter the cruise phase, during which it will travel through space towards Jupiter. This journey is expected to take about 6 years, during which the spacecraft will perform multiple gravity assist maneuvers around Earth and Venus to gain speed and adjust its trajectory. Jupiter arrival and orbital insertion. Upon reaching the vicinity of Jupiter, Europa Clipper will conduct a series of precise maneuvers to enter a highly elliptical orbit around the gas giant. This orbit will allow the spacecraft to perform regular flybys of Europa while minimizing its exposure to Jupiter's intense radiation belt. These flybys will enable the spacecraft to gather detailed data on Europa's surface and subsurface without the prolonged radiation exposure that a close orbit would entail. Flyby operations. The mission's primary scientific phase will involve around 45 close flybys of Europa, with the spacecraft passing within 25 to 100 kilometers 16 to 62 miles of the Moon's surface during each flyby. These close approaches will enable Europa Clipper's suite of scientific instruments to collect high-resolution images, surface composition data, and measurements of the Moon's ice shell and subsurface ocean. The flybys are strategically planned to cover different regions of Europa, maximizing the scientific return by providing a comprehensive survey of the Moon's diverse surface features and potential plume sites. Data collection and transmission. During each flyby, the spacecraft will gather a wealth of scientific data, which will be stored on board in high-capacity data recorders. After each flyby, the spacecraft will transmit this data back to Earth using its high-gain antenna. The mission team on Earth will analyze the data to build a detailed understanding of Europa's geology, chemistry, and potential habitability. This phase will involve continuous monitoring and adjustments to the mission plan based on the findings from each flyby. Extended mission and potential follow-up, depending on the spacecraft's health and the scientific discoveries made during the primary mission. NASA may opt to extend the mission for additional flybys and data collection. The findings from Europa Clipper will inform future missions, including potential landers or subsurface probes, to further explore Europa's habitability and search for signs of life. Throughout its journey, the Europa Clipper mission will leverage advanced navigation and communication technologies to ensure precise flybys and continuous data relay. The mission's success will rely on the collaboration of a global team of scientists, engineers, and mission planners dedicated to unlocking the secrets of one of the solar system's most intriguing moons. One of the primary goals of the Europa Clipper mission is to explore Europa's ice shell and the subsurface ocean it conceals. This investigation is crucial for understanding the moon's potential to support life, as well as its geophysical processes. Ice shell characterization. The ice shell covering Europa is believed to be tens of kilometers thick, but its exact thickness and composition remain uncertain. Europa Clipper will use ice-penetrating radar, specifically the Radar for Europa Assessment and Sounding, Ocean to Near Surface Reason, to probe beneath the surface. This radar will map the structure and thickness of the ice, revealing details about the layering and dynamics of the ice shell. Understanding the ice shell's properties is key to determining how material from the surface and subsurface may interact, potentially transporting nutrients and energy that could support life. Surface features and ice dynamics. Europa's surface is marked by a variety of intriguing features, including ridges, cracks, and chaotic terrain, where the ice appears disrupted and refrozen. These features suggest that the ice shell is geologically active, and may be influenced by the subsurface ocean. The Europa Imaging System eyes will capture high-resolution images of these surface features, allowing scientists to analyze their formation and evolution. By studying the surface features, researchers can infer the processes at work within the ice shell and how it may interact with the ocean below. Subsurface ocean exploration. Beneath Europa's ice shell lies a vast, global ocean, which is estimated to contain more water than all of Earth's oceans combined. This ocean is kept in a liquid state by the heat generated from tidal forces exerted by Jupiter's strong gravitational pull. The Europa Clipper mission aims to characterize this ocean by measuring its depth, salinity, and composition. The mission will use magnetometers to study the induced magnetic field created by the ocean, providing indirect measurements of its properties. Additionally, the plasma instrument for magnetic sounding PIMs will help characterize the plasma environment around Europa, further informing our understanding of the subsurface ocean. Plumes and surface interaction. Recent observations suggest that Europa may have water vapor plumes erupting from its surface, similar to those observed on Saturn's moon Enceladus. If confirmed, these plumes could provide direct access to the subsurface ocean. The Europa ultraviolet spectrograph Europa UVs will search for and analyze these plumes, determining their composition and potential links to the subsurface ocean. Analyzing the plumes can offer direct evidence of the ocean's chemical makeup and its potential habitability. Geochemical and geological insights. The mapping imaging spectrometer for Europa Massey will study the surface composition, identifying organic compounds, salt, and other materials that may originate from the ocean. These measurements will help scientists understand the ocean's chemistry and its potential to support life. Additionally, the Surface Dust Analyzer SUDA will examine particles ejected from Europa's surface, providing further insights into the Moon's geology and the materials present in the ice and ocean. Exploring Europa's ice shell and ocean is central to the mission's goal of assessing the Moon's habitability. By characterizing the ice, analyzing surface features, and probing the subsurface ocean, Europa Clipper will advance our understanding of this intriguing moon and its potential to harbor life. The data collected will inform future missions and contribute to our broader understanding of the conditions necessary for life in the universe. Europa, one of Jupiter's moons, is considered one of the most promising places to search for extraterrestrial life in our solar system. The Europa Clipper mission aims to investigate the potential habitats that could support life on this icy moon, focusing on several key aspects. Subsurface ocean. The most compelling habitat for life on Europa is its vast subsurface ocean, which lies beneath an ice shell that is believed to be several kilometers thick. This ocean is kept in a liquid state by heat generated from tidal flexing caused by Jupiter's strong gravitational pull. Similar to Earth's deep-sea hydrothermal vent ecosystems, Europa's ocean could harbor life forms that rely on chemical energy rather than sunlight. The ocean's potential for life is based on its long-term stability, availability of chemical energy, and possible nutrient mixing from the ocean floor and ice shell interactions. Hydrothermal vents. If hydrothermal vents exist on the ocean floor of Europa, they could provide the necessary conditions for life. On Earth, these vents support diverse ecosystems independent of sunlight, relying instead on the chemical energy from reactions between seawater and the rocky ocean floor. The Europa Clipper mission will use magnetometers and other instruments to detect anomalies in the magnetic field that could indicate hydrothermal activity. Understanding the presence and activity of these vents is crucial for assessing Europa's habitability. Surface-subsurface interactions. The interaction between Europa's surface ice and its subsurface ocean is another potential habitat for life. The ice shell may be dynamic, with areas where the ice has melted and refrozen, possibly allowing for nutrient exchange between the surface and the ocean. Features such as chaos terrain, where the ice appears to be broken and refrozen, suggest active processes that could bring nutrients from the ocean to the surface and vice versa. The Europa Imaging System eyes and the radar for Europa assessment and sounding. Ocean to near surface reason will study these features to understand the dynamics of the ice shell and its interactions with the ocean. Plumes of water vapor. Observations by the Hubble Space Telescope and other instruments have suggested that water vapor plumes may erupt from Europa's surface, similar to the geysers on Saturn's moon Enceladus. These plumes could provide direct access to the subsurface ocean, offering a way to study its composition without drilling through the ice. The Europa ultraviolet spectrograph Europa UVs will search for and analyze these plumes, determining their composition and potential links to the ocean. If these plumes contain organic molecules or other indicators of life, they would significantly bolster the case for habitability. Surface composition. The surface of Europa is coated with a variety of materials, including salts and possibly organic compounds, that may have originated from the subsurface ocean. The mapping imaging spectrometer for Europa Missi will analyze the surface composition to identify these materials and understand their origins. By studying the surface, scientists can infer the chemical processes occurring within the ocean and assess its potential to support life. Radiation effects. While Europa's surface is bombarded by intense radiation from Jupiter's magnetosphere, this radiation could create oxidants and other molecules that, if transported to the ocean, might serve as potential energy sources for life. Understanding how radiation affects Europa's surface and subsurface environments is crucial for assessing its habitability. The mission will measure the radiation environment and its impact on surface chemistry. Exploring these potential habitats will help determine if Europa's ocean and its interactions with the ice shell create the conditions necessary for life. The data collected by Europa Clipper will provide a comprehensive understanding of the Moon's habitability and guide future missions in the search for life beyond Earth. The Europa Clipper mission, while groundbreaking in its objectives, faces several significant challenges and risks that must be carefully managed to ensure its success. These challenges span from technical and engineering hurdles to the harsh environmental conditions around Jupiter and its moon, Europa. Radiation environment. One of the primary risks is the intense radiation environment around Jupiter. Europa lies within Jupiter's powerful magnetosphere, which traps high-energy particles. This radiation can damage the spacecraft's electronics and instruments, degrading their performance over time. To mitigate this, Europa Clipper is designed with robust radiation shielding and uses radiation-hardened components. The mission plan also includes a highly elliptical orbit to minimize the time spent in the most intense radiation zones. Extreme cold. Europa's surface temperatures average around -160 degrees Celsius, -260 degrees Fahrenheit. Such extreme cold can affect the performance of the spacecraft's instruments and systems. Engineers have developed thermal control systems to keep the spacecraft's components within operational temperature ranges. Insulation, heaters, and radiators are used to manage the thermal environment of the spacecraft. Complex flybys. The mission involves multiple close flybys of Europa, requiring precise navigation and timing. Each flyby needs to be carefully planned and executed to ensure that the spacecraft collects the necessary data while avoiding collision with the Moon's surface. These maneuvers are complicated by the gravitational influences of Jupiter and its other moons, which can alter the spacecraft's trajectory. Advanced autonomous navigation systems and detailed trajectory planning are critical to managing these challenges. Data transmission. Given the vast distance between Earth and Jupiter, transmitting data back to Earth poses another challenge. The spacecraft will collect large volumes of scientific data during its flybys, which need to be transmitted across approximately 600 million kilometers, about 373 million miles. The mission utilizes a high-gain antenna and advanced communication systems to send data back to Earth. However, the data transmission rate is limited, requiring efficient data management and prioritization strategies. Power supply. Operating in the outer solar system, far from the Sun, limits the availability of solar power. Europa Clipper relies on large solar arrays to generate power, but the reduced sunlight at Jupiter's distance means that power generation is significantly lower than for missions closer to the Sun. The spacecraft must manage its power consumption carefully, prioritizing essential systems and instruments during critical mission phases. Instrumentation and payload. The mission's scientific payload includes a suite of advanced instruments, each with specific requirements and sensitivities. Ensuring that these instruments function correctly in the harsh conditions of space and during the flybys requires meticulous calibration and testing. Additionally, the instruments must be protected from contamination that could compromise their measurements. Potential for plume interactions. If Europa Clipper encounters plumes of water vapor during its flybys, there is a risk of impacting small particles or droplets. While these encounters are scientifically valuable, they also pose a risk to the spacecraft's instruments and systems. Engineers have developed protective measures and operational strategies to minimize this risk while maximizing scientific return. Operational lifetime. The cumulative effects of radiation, cold, and the mechanical stresses of numerous flybys may limit the spacecraft's operational lifetime. Careful planning and engineering are essential to extend the mission's duration and ensure that it can complete its scientific objectives. By addressing these challenges through innovative engineering, careful planning, and robust risk management, the Europa Clipper mission aims to overcome the harsh conditions of the Jovian system and achieve its ambitious goals in the search for life beyond Earth. The Europa Clipper mission is expected to make significant discoveries that could reshape our understanding of Europa and its potential for life. These discoveries could have far-reaching implications for astrobiology, planetary science, and our broader understanding of the solar system. Confirmation of a subsurface ocean. One of the most anticipated discoveries is the confirmation of Europa's subsurface ocean. While strong evidence suggests the presence of a global ocean beneath the Moon's icy crust, direct confirmation would be groundbreaking. The composition, depth, and dynamics of this ocean would provide crucial insights into Europa's potential habitability and the prevalence of liquid water in the outer solar system. Characterization of the ice shell. Europa Clipper is expected to provide detailed information about the ice shell covering Europa. This includes its thickness, composition, and structure, which can help scientists understand the interactions between the surface and subsurface ocean. The ice shell's properties are key to assessing the potential for material exchange, energy transfer, and habitability within the Moon. Identification of potential habitats. The mission aims to identify potential habitats for life on Europa, including regions where the subsurface ocean may interact with the surface. Features such as chaos terrain and potential hydrothermal vents could provide niches where life could thrive. Discovering these habitats would not only inform our understanding of Europa, but also expand our knowledge of habitable environments beyond Earth. Chemical and geological insights. Europa Clipper will analyze the surface composition, looking for organic compounds, salts, and other materials that may originate from the subsurface ocean. These findings could provide clues about the ocean's chemistry and its potential to support life. Additionally, the mission will study the Moon's geology, shedding light on its past and present geological processes. Implications for astrobiology. The discoveries made by Europa Clipper could have profound implications for astrobiology. Finding evidence of a subsurface ocean, habitable environments, or even signs of life on Europa would suggest that life may be more common in the universe than previously thought. It would also raise questions about the potential for life on other icy moons in the solar system and beyond. Future exploration. The data collected by Europa Clipper will pave the way for future exploration of Europa and other ocean worlds. This could include missions to land on Europa's surface, deploy submersibles to explore its subsurface ocean, or even return samples to Earth for detailed analysis. The discoveries made by Europa Clipper will guide and inspire future missions to explore these fascinating worlds. Overall, the Europa Clipper mission is poised to make groundbreaking discoveries that could revolutionize our understanding of Europa and its potential for hosting life. The implications of these discoveries extend far beyond the confines of our solar system, opening new avenues of exploration and discovery in the search for life elsewhere in the universe. The Europa Clipper mission represents a significant step forward in our exploration of Jupiter's moon Europa, but it is just the beginning of what promises to be a long and exciting journey of discovery. The data collected by Europa Clipper will not only inform our understanding of Europa, but also shape the future of exploration on this intriguing moon. Potential follow-up missions. The discoveries made by Europa Clipper are expected to pave the way for future missions to Europa. These missions could include landers or even submarines designed to explore the Moon's subsurface ocean. By directly sampling the ocean and seafloor, these missions could provide definitive evidence of habitability and even search for signs of life. Sample return missions. Another possibility is a sample return mission, which would collect samples of the surface or subsurface materials from Europa and return them to Earth for detailed analysis. These samples could provide unprecedented insights into Europa's geology, chemistry, and potential for life. International collaboration. Europa exploration is likely to involve international collaboration, with space agencies from around the world contributing expertise, resources, and technology. This collaboration could lead to more ambitious missions and a greater understanding of Europa's potential for life. Technological advances. Advances in technology, such as improved propulsion systems, autonomous navigation, and miniaturized instruments, will also play a crucial role in future Europa exploration. These advances will enable more efficient and capable missions to Europa and other ocean worlds in the outer solar system.
Astrobiological significance. The discoveries made on Europa could have profound astrobiological significance.
Not only for understanding the potential for life on Europa, but also for informing our search for life elsewhere in the universe. Europa's subsurface ocean is considered one of the most promising environments for life beyond Earth, and studying it could provide valuable insights into the conditions necessary for life to exist elsewhere in the cosmos. In conclusion, the future of Europa exploration is bright, with the potential for groundbreaking discoveries and new insights into the mysteries of our solar system and the universe beyond. Europa Clipper is just the first step in this journey, and the discoveries it makes will shape the direction of future missions and our understanding of this enigmatic moon.